Pluto, the enigmatic dwarf planet residing at the farthest reaches of our solar system, continues to captivate the astronomical community despite its reclassification from a full-fledged planet. Recent developments have sparked renewed interest and concern among scientists and space enthusiasts, as some reports hint at a possible future encounter between Pluto and Neptune, raising alarms over the potential consequences of such a celestial event. Renowned experts such as Neil deGrasse Tyson and Michio Kaku have expressed their thoughts on the implications of a potential collision between these two distant celestial bodies, prompting many to ask how Pluto's path might intersect with Neptune's and what this could mean for the broader solar system and even for Earth itself. This raises questions about the orbital dynamics that govern these planets and the cosmic ballet that has kept such a collision at bay for billions of years. To understand the present concerns and the mechanisms that might prevent or facilitate a potential collision, it's essential to dive into Pluto's complex orbit, the forces acting upon it, and the implications of any disruption in the delicate gravitational balance. Once considered the ninth planet in the solar system, Pluto's status shifted in 2006 when the International Astronomical Union (IAU) reclassified it as a dwarf planet. This change in classification was largely due to Pluto's unique characteristics and its failure to meet all the criteria set out by the IAU for full planetary status. Despite this change, Pluto's journey through space continues to intrigue astronomers, especially due to its highly elliptical orbit and its interaction with Neptune's path. These characteristics set it apart from other planets in the solar system, whose orbits are more circular and lie closer to the ecliptic plane, the imaginary flat surface that aligns with Earth's orbit around the Sun. Pluto, on the other hand, follows a much more tilted and elongated trajectory, which occasionally brings it closer to the Sun than Neptune. This unusual orbital pattern, combined with the gravitational influences of nearby planets like Neptune and Jupiter, has led to an intricate cosmic dance that has prevented collisions thus far. But could this balance be disturbed in the future? Pluto's orbit around the Sun takes an astonishing 248 years to complete, meaning it has not yet made a full revolution since its discovery in 1930 by Clyde Tombaugh. Adding to its mystery is the steep 17 degrees inclination of its orbit compared to the nearly flat orbits of the major planets. This makes Pluto's path significantly steeper relative to the ecliptic plane, where most of the solar system's planets orbit. Another important aspect of Pluto's orbit is its elliptical nature, which differs from the near-circular orbits of other planets. As a result, Pluto occasionally ventures inside Neptune's orbit, coming closer to the Sun than Neptune for about 20 years during each revolution around the Sun. This oddity raises the question, why has Pluto never collided with Neptune during its long journey through space? The answer lies in the gravitational interactions between the planets, particularly the mechanism known as a mean motion resonance. Pluto and Neptune are locked in a 3:2 orbital resonance, meaning that for every 3 orbits Neptune completes around the Sun, Pluto completes 2. This resonance ensures that even though Pluto's orbit crosses Neptune's path, the two celestial bodies are never close enough to collide. In fact, when Pluto reaches the point in its orbit where it crosses Neptune's path, the resonance ensures that Neptune is always far away, either ahead of or behind Pluto in its orbit. This delicate balance, governed by the gravitational influences of the Sun and the giant planets, has kept Pluto and Neptune in their respective orbits for billions of years without incident. Astrophysicists often refer to this kind of resonance as part of a broader phenomenon known as the three-body problem, which describes the complex gravitational interactions between 3 celestial bodies, such as Pluto, Neptune, and the Sun. These interactions create a dynamic system in which the paths of the planets are shaped by the gravitational pulls of each other. However, the three-body problem is notorious for its complexity, as it involves understanding how the gravitational influences of multiple objects interact over time. This leads to what is often called orbital chaos, where even small changes in initial conditions, such as a planet's position or velocity, can lead to drastically different outcomes over long periods. One important factor that prevents a collision between Pluto and Neptune is a phenomenon known as the Kozai mechanism, which causes oscillations in a planet's orbital elements, particularly its inclination and eccentricity, the degree to which an orbit is elliptical. For Pluto, this mechanism helps keep its orbit stable over long periods, ensuring that even though its path crosses Neptune's orbit, the two planets never come close enough to collide. Additionally, Pluto's latitude libration, the oscillation of its position relative to the plane of the solar system, ensures that when Pluto crosses Neptune's orbit, it is always positioned significantly above or below Neptune, adding another layer of protection against collisions. Numerical simulations conducted in the late 1980s and 1990s helped scientists understand how Pluto's orbit has remained stable despite its chaotic nature. These simulations revealed that while Pluto's orbit is technically chaotic, meaning small deviations in its initial conditions could lead to significant changes in its path over millions of years, the orbit remains stable over incredibly long time scales. This stability is due in large part to the gravitational influences of Neptune, Jupiter, and Saturn, which help to keep Pluto's orbit in check. In particular, the 3:2 resonance with Neptune plays a critical role in maintaining this stability, as it prevents the two planets from coming too close to each other. The interplay of these gravitational forces has led to what astrophysicists call a dynamically protected orbit, where Pluto's path is shielded from collisions with Neptune thanks to the resonance and the Kozai mechanism. Jupiter's immense gravitational influence also contributes to the stability of Pluto's orbit, while Saturn plays a smaller but still significant role in shaping the orbital dynamics of the outer solar system. These combined forces ensure that Pluto's orbit remains stable for billions of years, despite the chaotic nature of its trajectory. However, despite this long-term stability, some scientists have raised concerns about the possibility of a future collision between Pluto and Neptune. While the current understanding of celestial mechanics suggests that such an event is highly unlikely, the chaotic nature of Pluto's orbit means that small changes in its path could, in theory, lead to a close encounter with Neptune at some point in the distant future. Renowned astrophysicist Neil deGrasse Tyson has weighed in on the issue, emphasizing the importance of understanding Pluto's complex orbit and the gravitational forces that govern its movement through the solar system. Tyson, who played a key role in the reclassification of Pluto as a dwarf planet, views Pluto's unique orbit as a reminder of the complexities and mysteries of celestial mechanics. Tyson's perspective on Pluto's orbit is shared by other prominent scientists, including Michio Kaku, a theoretical physicist known for his work in string theory and popular science. Kaku has highlighted the potential implications of a Pluto-Neptune collision, not just for our solar system but for the broader understanding of celestial mechanics and theoretical physics. According to Kaku, studying the gravitational interactions between Pluto, Neptune, and other planets can provide valuable insights into the fundamental laws of physics, including string theory, which seeks to explain the behavior of matter and energy at the most basic level.